Welcome back, folks, and welcome to our online students. Today what we're going to do is look at some examples of intermolecular forces and use intermolecular forces to make some predictions about molecules, kind of comparing them back and forth. But this was a little while ago since we got together, and so I want to just try to do just a brief review on intermolecular forces. So, intermolecular forces. Intermolecular forces. Intermolecular forces. There's several different types of intermolecular forces, and some of them have different strengths, or they have different strengths as compared to each other. So I'm going to put strength here. S-T-R-E-N-G-T-H. Strength. And so I want to rank these things. I want to rank my intermolecular forces. So help me out here. Name me one intermolecular force. One intermolecular force. Yes. Hydrogen bonding. Awesome. That is a great intermolecular force. We'll call that hydrogen bonding. Okay. Hydrogen bonding. Awesome. One other. Another intermolecular force. Dipole, dipole. Dipole, dipole. Nice, nice. Anything else? Any other intermolecular forces? Yeah. London dispersion forces. London dispersion forces. And what do they call those things in Germany? Anybody remember? Van der Waals forces. Okay, same thing. Van der Waals forces if you're German. Okay, so these are our three main intermolecular forces. There's a fourth one that we kind of squeeze in here sometimes. We have a fourth one. Thank you for helping. Ionic. It's got ion in it, yeah. Ion dipole, yeah. Ion dipole is an intermolecular force, and it kind of fits in here, but it's a little fuzzy. And so some people will put it here, ion dipole. And some people will put it here. And truth be told, it's an intermolecular force that's kind of in the range here of hydrogen bonding. And we're really not going to spend much time talking about ion dipole, but it is a thing, and it's right around in this area as far as strength goes. Thank you for making sure we didn't forget that one, right? Okay. So here are our different intermolecular forces, and if we want to say something a little bit about these things, hydrogen bonding. If you have hydrogen bonding, you must have what element? Please say hydrogen, please say hydrogen, please say hydrogen. Hydrogen! We have to have hydrogen for hydrogen bonding. But that hydrogen must be bonded to something very specific. There's three things that it can be bonded to. One of three things. Oxygen is one. Yep, so hydrogen bonded to oxygen will form hydrogen bonds. Hydrogen bonded to nitrogen is another one. And then hydrogen bonded to fluorine. Okay. Fluorine. So it has to be bonded to one of these three elements, and we can do hydrogen bonding, or we can have hydrogen bonding. Now, dipole, dipole, this is between polar molecules. So you have to have two polar molecules. So we'll say here, between polar molecules. Between polar molecules. Okay, so like water. Water is polar, and so we could have dipole, dipole with water. And then London dispersion forces. These could be atoms or molecules. Atoms and molecules. Okay. And if you remember from the last time we got together, the bigger the atom or the bigger the molecule, the more London dispersion forces. And these London dispersion forces are weak. Dipole-dipole are stronger, and hydrogen bonding is the strongish intermolecular force. Okay, so that's kind of a review. That is like everything we talked about the last time we got together in a nutshell. So now, can we identify some properties of things here? Well, let's see. It says, which pure substance will not form hydrogen bonds? Oh, that's a great test type question. And you look up there and you see hydrogen in all of them. And you go, oh, well, clearly all of them will hydrogen bond because they all have hydrogen, because it's hydrogen bonding. But one of them doesn't. And so the brain kind of drifts and say, okay, well, which one's different? And you might look and you see the nitrogen there and you go, oh, well, nitrogen's different than the other three, right? The other three don't have nitrogen. So clearly it can't be C. But you'd be wrong. So which one is it? This is a little tricky to try to answer if you can't actually see the molecules. Oh, yeah, behind, yes. Yes, glasses, yes. Awesome. Okay, so you're saying B seems most likely because there are hydrogens, but they are bonded to the carbons and not to the oxygen. And that is correct. So it has an oxygen, it has a hydrogen, but they're not bonded to each other. So B will not hydrogen bond. Nicely done. Nicely done. Now A has an oxygen and a hydrogen, and they are attached to each other. And then C, we have a nitrogen attached to a hydrogen. And then D, we have an oxygen attached to a hydrogen. And so the one that does not hydrogen bond is B by itself. Nicely done. All right. About this, what kinds of intermolecular forces exist in these molecules? Okay, so if we had like a bucket of each of these, what kind of intermolecular forces would there be? Now, sometimes you have to draw out the Lewis structures in order to identify these things. So as we take a look at these, we'll take a look at A. Carbon tetrachloride is carbon, and then it has 4 chlorines, like this, carbon tetrachloride. And what kind of intermolecular forces do we have? Okay, well, here's a hint. Whenever you're asked to identify the intermolecular forces that something has, everything has London dispersion forces. So if you're not sure and you have to guess, put London dispersion forces because you can't be wrong. Everything has London dispersion forces. So I'm just going to write here London dispersion forces, okay, because everything's got that. And then how about the next one here? Dipole-dipole. Is this a polar molecule? Well, maybe let's take a step back here. The bond between the carbon and the chlorine, is that polar? Is there an unequal distribution of electrons between carbon and chlorine? Yeah. Chlorine is more electronegative. And so if we were to draw a force line, it would look something like this for each one of these. Chlorine is more electronegative than is carbon. Okay, so we have polar bonds. Is the molecule polar? Molecule is not polar. You are correct. Why is the molecule not polar? But they're equal and opposite. Yeah, they're equal and opposite. Now, this is drawn in 2 dimensions. This would actually be tetrahedral. But either way, these forces are equal and opposite, and therefore this molecule is nonpolar. So it's not dipole-dipole. And then hydrogen bonding. Clearly not hydrogen bonding because we don't have hydrogen. Right? Okay. So those are the only forces present in carbon tetrachloride. How about the next one here? That looks like acetic acid. So carbon with 3 hydrogens, a carbon that's double bonded to an oxygen, and then single bonded like that. Okay, to an OH. There's acetic acid. London dispersion forces? Y'all better say yes. Okay. Dipole-dipole, is this a polar molecule? Do we have a strongly electronegative element? Yes, we have oxygen. And is it equal and opposite? So like we have oxygen here pulling electrons towards itself and electrons being pulled towards oxygen. Are these equal and opposite? No. So this is a polar molecule. So I'm going to say London dispersion forces. It is a polar molecule, so I'm going to go dipole, dipole. And then lastly, do we have hydrogen bonding? Do we have hydrogen bonding? Yes, yes we do. We have an O attached to an H here. We have an OH bond right there. Okay, so we would have hydrogen bonding. So H bonded. Okay, and then the last one here, H2S. So S, hydrogen, hydrogen, couple of lone pairs, looks like that. Okay. All righty. Shoot, I was going to pick on the people with hats, but you already answered questions. But you haven't. Twins. Yeah, it's hard to be a Vikings fan right now, right? That was a tough night. Okay. So help me out here. Intermolecular forces. Does it have dispersion forces? Yeah, darn right it does. Everything does. London dispersion forces. Okay. How about dipole-dipole? Is that a polar molecule? Yep, it's a polar molecule. We have sulfur, which is more electronegative than hydrogen. We've got looking like this. Okay, and so this is a polar molecule. We'll call this dipole, dipole. Okay, and then lastly, hydrogen bonding. Do we have hydrogen bonding? No, no. But it's got hydrogens. There's no oxygen, nitrogen, or fluorine attached to it. Nice. Okay, excellent. So no hydrogen bonding. Nicely done. Any questions on that? Okay. All right. What type of intermolecular forces must be overcome in converting each of the following from a liquid to a gas? We've got liquid oxygen, methyl iodide, and ethanol. Okay. All right, so here, give this one a try. Try drawing out the Lewis structures for these 3 molecules and identify the strongest intermolecular force attracted between each of those, the attraction between each of these.
A few minutes later.
Oxygen. Help me out here. Oxygen. Lewis structure. Can you help me with the Lewis structure for oxygen? Draw 2 oxygens, okay? And double bond. Yep. Yeah, nice. And we could get fancy and throw a couple lone pairs in there. Okay, so there's our oxygen gas, okay, or liquid oxygen. Now, for our London dispersion forces, for our intermolecular forces, what would they be? What could we have for intermolecular forces here? London dispersion forces, because everything has that. London dispersion forces, okay. Anything else? Anything else? No, that's it. Yep, that's all it has. So the strongest intermolecular force is London dispersion forces, which is fairly weak. It's fairly weak. Okay, nicely done. This is why oxygen is typically a gas at room temperature, because it has very little force holding those molecules to each other. Okay, how about methyl iodide? methyl iodide. Oh, man. You know, you already answered a question, but right behind you, hey, Daniel, could you help us out here? Methyl iodide, could you help us with the Lewis structure for that? Carbon in the center. 3 hydrogens, okay. And then iodine over here. Okay, excellent. Nicely done. Okay, so intermolecular forces. London dispersion, okay. London dispersion forces, okay. Dipole, dipole. Because it is a polar molecule, iodine is more electronegative, and so we have our unequal distribution of electrons. Nice. And anything else? That's it, because there's no hydrogens. Well, there's hydrogens, but they're not attached to an oxygen, nitrogen, or fluorine. Okay, nicely done. Ethanol. Help me out with ethanol. Hey, you help me out, okay, already, right? Yeah, okay, how about right behind you? Al, could you help me out with that one? Okay, so ethanol. Let's do, can you help me with the Lewis structure for ethanol? It's got 2 C's, yep. So hydrogen on every side. 2 on the second one, okay. Up and down, okay. Yep. Okay. Okay, like that. Yeah, okay, yep, that looks good. Okay, so now for our intermolecular forces. Hydrogen bonding, because we have oxygen and hydrogen there. Okay, nice. London dispersion forces, okay. Dipole, dipole. Dipole. Okay, excellent. Nicely done. Okay, so this one's got all of them. It's got everything. Nicely done. Here's a question for you. Ethylene glycol is one of the main ingredients in antifreeze. Would you predict its viscosity to be greater or less than that of ethanol? Now, viscosity is just a measure of resistance to flow, or we could think of it as being stickier. The stickier it is, or the stronger the force between the molecules, the greater the viscosity. So between ethylene glycol and ethanol, which one is going to be stickier? What do you think? Yeah, what do you think? Ethylene glycol, because it has more hydrogen bonds. Excellent. Yeah, so it's got hydrogen bonded to oxygen, so it forms hydrogen bonds. So does the ethanol, but the ethylene glycol's got 2 of them. Yes, and so yes. The ethylene glycol would have stronger intermolecular forces, would be more viscous. It also then would have a higher boiling point. This is why for your radiator in your car, you might use ethylene glycol and not alcohol. Okay? Now another funny, odd thing about ethylene glycol, does anybody know what it tastes like? I know, it's just kind of an odd question. Anybody know what ethylene glycol tastes like? Yeah. Yeah, it tastes sweet. It does taste sweet. So its molecular structure, when it hits the tongue, it hits the same receptor sites as the sweet. And so if you taste ethylene glycol, it tastes sweet. And if you've ever seen antifreeze, it looks like Gatorade. And it tastes sweet. And this is really dangerous because it's really, really toxic. And so they recommend that you not have this sitting around where kids can get into it or dogs. Okay, rank the following compounds in order of increasing boiling point. Increasing boiling point. So the structure that would have the highest boiling point would be the stickiest one. The one with the lowest boiling point would be the least sticky. The least sticky. As we look at these three molecules, what do we see? Okay, getting some head bobs over here. What are you thinking? Okay, just stop for a second. Okay, so you said the middle one has no hydrogen bonds. It has hydrogens, but not attached to these things. Okay, right? Okay, so that'll be a weak one. Okay, excellent. Continue. So the one on the right has one. Oh, I'm sorry, the left. Okay, so the left one there has an oxygen attached to a hydrogen. So that's one, and that'll be a hydrogen bond. That's pretty strong. Okay.